We're going to finish, and then we're just going to get a start on the next chapter. We're definitely not going to finish this whole section that I handed out today. We'll start it today and probably finish it on Monday. Before I do that, before we get started, are there questions? Any questions folks would like to ask? Hearing none, and I guess I didn't do an AV check with you guys. I heard Jason talking. You all have microphones that you can use?
Yeah, we have microphones.
Yes.
Okay, perfect. All right, then that means I'll take the silence as a sign that there were no questions. Okay, so let's kind of pick up where we left off. All right, so the last thing we did was we solved a differential equation by using integration. It was something that we could kind of solve by integrating. And we're going to spend a lot of time in this course. A bulk of our time is just going to be how do we solve different kinds of differential equations and identify what we know a family of functions ought to look like, and then how we can go ahead and solve the, find a particular solution. So, let's see. All right, so this is where we are. So if we think about this differential equation right here, x prime equals x, we're looking for a function that's equal to its own derivative. And from Calc 1, really, we know a function equal to its own derivative is why it's our favorite function, and that's the exponential function with a natural base. It has to be the natural base. Any other base is not going to be equal to its own derivative because you have to have that, like the derivative of like 2 to the t instead of e to the t is 2 to the t times ln 2. Right, like so. If it's any other base, we have to have this constant factor that we throw in there. So the natural exponential function is the only one that works. So e to the t works. It might not be entirely obvious, although it's pretty simple to check, that any function of the form c times e to the t will work. So where c is any constant, that'll work because we just bring down constant factors, right? When we take derivatives. And in fact, this is the general solution. Not only does this work for any value c, but if any function is going to work, it will take on that form. So it's a one-parameter family of solutions where c is the parameter. And it's a general solution, meaning that anything that will work will be of that form. So let's solve this initial value problem. They're giving us x prime equals x, and that x of 0 is equal to a half. So we already know the general solution. Kind of figured that out by inspection. We just need to find c. That's the general solution. They gave us an initial value so we could find the particular solution. So x of 0 equals a half means that 1/2 is equal to c e to the 0. And of course e to the 0 is 1, so 1/2 is equal to c. And now we could put that into the function. There's our particular solution. Let's try another one. Here's a second order differential equation, x double prime equals negative x. So we're looking for a function whose second derivative is equal to the negative of that function. It's probably not obvious, although it's not difficult to show or to check, that this function, this family of functions, is a solution. In fact, I'm pretty sure that it's a general solution, meaning any solution to that equation will take on that form. So it makes sense that we see like a sine term and a cosine term, at least it does for me, like the derivative of sine is cosine and then its derivative is negative sine. Like by the time you get to the second derivative, it's just the negative of the function. And that's true for cosine as well. The derivative of cosine is negative sine, and then the derivative of negative sine is negative cosine. So it works for these individually, which means if we put them together as terms by adding them, not multiplying them, but by adding them, that sum will be a solution. And there are two parameters now, C1 and C2. When we had the first order differential equation, there's only one value that we needed to get an initial value problem, right? Just tell me one value of the function. A lot of times it's at 0, but it could be anywhere. When you have a second order differential equation, we actually need 2 bits of information. We need to know the value of a function at a point and the value of its derivative at a point. To be an initial value problem, it's got to be the same point. It's not like crucial that that point happened to be 0, but it has to be the same value of t. Otherwise, it's called a boundary value problem. Like if I knew x at t equals 0 and x prime at t equals 1, that would be called a boundary value problem. And generally, those are a little bit harder to solve. So let's solve this initial value problem. So we know we have our general solution. And we can just use each of these values that they gave us. So they told us that x of 0 equals 2. So let's see what that gives us. So 2 equals C1 sine of 0 plus C2 cosine of 0. 0 is a pretty convenient value. Sine of 0 is 0. Cosine of 0 is 1. So that's 0. This is 1. So 2 is equal to C2. So plugging in that first bit of information that x of 0 is 2 is pretty simple. How do we use the other one? How do I plug in x prime of 0 is equal to negative 1?
Do you take the derivative of x?
Yeah, I think I heard a couple people say this, but yeah, we're going to just find x prime of t, right? And then we can plug in a value for t. So what do we get for x prime of t as a function?
C1 cosine of t minus C2 sine t.
C1 cosine t minus C2 sine t. Yeah, good. So now that we have that as a function, we can go ahead and use the other bit of information they gave us. X prime of 0 is equal to negative 1, so then negative 1 is equal to C1 cosine of 1 minus C2, oh no, not cosine of 1, cosine of 0, sorry, minus C2 sine of 0. Again, 0 is pretty convenient, so sine of 0 is 0, that'll go away. Cosine of 0 is 1, so C1 is equal to negative 1. And now that we have both of those values, we just rewrite our function with the known parameters. How's that? Okay. So before we start the next section, I'll just alert you to, so you might already have seen this, but our first assignment is up. So assignment 1 is posted to Canvas. There's some problems with that are like the ones we did, where we're just, that we did last time, where we're verifying, show that this is a solution. You can show that a function and its derivative, when we plug them in, satisfies the equation. Solving an initial value problem, and we know the general solution. And then there's going to be a couple problems from what we're going to cover today. So you'll find that on Canvas. If you go to Canvas, actually, and just click on assignments, then you'll see it right here, and there's a PDF that you can print out. Please do print it out and use it as a cover sheet for your assignment. It's due a week from today. All right, so chapter 2 is all about looking at first-order differential equations. So differential equations that just involve a function and its first derivative. And we're going to focus first on those that are separable. The ones that are separable are ones that we can solve by doing some integration. So a first-order equation is separable if, and again, I'm thinking about this function, I'm using x as a function of t. So dx dt can be written as g of t times h of x, where g of t is a function only of t, h of x is a function only of x. So you can kind of see it as a product of these two distinct functions, where I've got just t's and just x's. I think of them as separable. Like when I think of separable, the way I think about it is I can actually separate it on different sides of the equation. So I could have all my x's with my dx and all my t's with my dt. And we call that process separating the variables. And if you could separate the variables, then theoretically, as long as it's something that we know how to integrate, we can solve by integration. So we're going to do a little bit of just checking to see which ones of these are separable, kind of recognizing when something is separable. And then we'll do some solving differential equations. So this first one, x prime is x times t plus 2x. Is it possible to write that as just a function of x's times just a function of t's? And how would we do it?
X prime over x equals t plus 2.
Okay, so you divided both sides by x. Yeah, we could do that, because that groups the x prime with the x. I'm going to kind of think of it in these terms first, and then kind of go through and I think get to what you're talking about. But so we have our dx dt on this side, and it should be just some function of x's times some function of t's. And you talked about, you alluded to dividing by an x. What that tells me is we could actually factor out an x on this side. So in the definition, in the I guess notation of the definition, our g of t function would be t plus 2, and our h of x function is just x. Now, if we think about actually separating them out, so we have the x's with the dx and the t's with the dt, all we would need to do is multiply both sides by dt over x. We don't need to do this to determine if it's separable, but it is it is something we would do to go ahead and solve it if that's what we're going to do. And then we'd have, what, t plus 2 dt. And we'll get some practice solving these in a bit. But notice that on this equation that we've just written, my dx's are with the x, my dt is with the t's. There's no mixing of t's and x's on any side of the equation. So this one, I guess just to answer the question, is separable. How about the next one? can we write that right side as a function of x's times a function with t's? No. Yeah, I agree. We can't. What we have is a function of x's plus a function with t's, but that's not good enough. That's not what we need for it to be separable. So this is not separable. We just can't do it. Let's do the next one. So x prime is by itself on the left side, so our goal is on the right side. Can I write that as just some stuff with t's multiplied by just some stuff with x's? Like basically, can we factor it in a way where I have t stuff times x stuff? So I'm going to consider this. Start by kind of trying to group it that way.
Factor out the t squares on that first side there.
Mm-hmm.
Yeah.
Like that?
And then factor out the t's on the other one.
Yeah. Because where can we go from here now? Yeah, we'll take out the x plus 1. That's a common factor now. So we have x plus 1 times t squared minus t. So this is separable. In the notation of the definition on the last page, we would say that g of t is t squared minus t. H of x is x plus 1. All right, last one. Is this separable? No? Why? Okay. I mean, there's no actual t, but we could say there's certainly a function of t. Like, and this is going to feel like, I don't know if it's going to feel like cheating, but that function of t is just the constant function, 1. G of t is 1. That's still separable. So working with a first order differential equation, we kind of have, I mean, mostly I guess it's a question of algebra, try to see if something's separable. You know, can we arrange the terms and factor things in a way that we can kind of segregate out the factors of x from the factors of t. If we have a separable equation, and we solve just by separating those variables, getting the x's together with the dx on one side and the t's together with the dt on the other side. Whenever we're solving a differential equation by integrating, we have to make sure we add the constant immediately upon integrating. Like in Calc 1 and Calc 2, you know, the integration that we do, we're used to being able to just like do the plus c at the very end. And we know we're going to be fine because, oh, plus a constant on the end. But the way that that constant gets worked in, you know, once we integrate first, we're not done the problem, and then we have to keep doing a bunch of algebra. So like where that constant kind of then ends up showing up in the final answer is different. And you get something really different than just tacking on a plus c at your very last step. So we're going to do some examples. We're going to integrate and solve some differential equations. So here x prime of t is minus t x squared. When I'm solving by separating variables, I always rewrite that function in the dx dt form instead of the prime notation. This is separable. We could, I mean, obviously, right, negative t is our function of t and x squared is our function of x. So I'm going to just segregate these out so that my x's are with the dx and my t's are with the dt. And by the way, dx and dt, they're always on top. They're never on the bottom. So like I'm definitely going to multiply by dt on both sides. So I'm going to have my t's and dt on the right side here. So I want to get rid of that x squared. So in fact, I'm going to multiply by dt over x squared. And after we cancel what we'll cancel, we are end up with x to the negative 2 dx. And on the other side, those x squareds cancel, so we have minus t dt. What do we do now?
Integrate.
Yeah, integrate. So if we integrate x to the minus 2, that's a power. They're both power rule integrals. We get x to the negative 1 over negative 1, or negative x to the negative 1. On the other side, what do we get? Yeah. Plus a constant. Now this constant might change, so as soon as I add a constant, I almost always subscript it, because as I work through this problem, I might kind of replace one constant with another, and I just want to make sure that I'm using distinct constants when I need to. So, all right, we've done the integration. Now there's going to be a bunch of algebra and rearranging to do to get x of t, find x as a function of t. So this is on the left side, negative 1 over x. I want to solve for x. If I know what negative 1 over x is, like, what is x? We'll worry about cleaning it up, you know, as after we do this first initial step. But like, how do I go from here to here on the other side?
Negative 1 over everything.
Yeah, negative 1 over the whole thing. Now, that is what x is equal to. That's not really simplified. It's really kind of not very satisfying to look at. So let's clean it up a little. I don't like fractions within fractions. I mean, nobody does. I know you don't either. So let's just take care of that. I'm going to multiply top and bottom of this right side by negative 2. When we do that, now I've got my function x, or I'll just go ahead and call it x of t now, is positive 2 over t squared Now, you might write minus 2 times C1, and you could do that, that's fine, but negative 2 times an arbitrary constant is just another arbitrary constant. So I'm just going to call this plus C2, or even just plus C. Maybe just drop the subscript. There's my function. So notice it was really important that we added that constant of integration right up here, right at the very get-go. Like the result, the final result for x of t is not something with t's and then plus c at the end. Like look at how this constant showed up at the bottom. Are there questions on this example? Okay. All right. Let's do another. We're going to do a bunch of problems today. Right, so x prime of t is t times x plus 1. Again, could somebody point out to me how I know that that's separable?
ut is t and hx is x plus 1.
Yeah, right. We just have a product, something only t's times something only x's. Yeah. So I'm going to rewrite this with the dx dt notation. And then t times x plus 1. How do I separate them out? What should I do to get all of my x's with the dx and my t's with the dt?
Well, you could multiply the dt and divide the x plus 1.
Yeah, good. Multiply by dt and divide by x plus 1. So now we have dx over x plus 1 is equal to t dt. Now that they're separated, let's see if we can't integrate. What do we get on the left? Yeah, good. Ln of absolute x plus 1. How about on the other side? Mm-hmm. And then plus a constant. So, again, remember our goal is to get x of t equals some function of t. Right now my x is stuck inside a ln function. So what do we do? Yeah. So if ln of this stuff is equal to the right side, we just write the exponential form of this. And we say absolute x plus 1 is equal to e to the 1/2 t squared plus c1. We're getting closer because now x is no longer trapped inside the ln. It is not by itself, and it's stuck inside an absolute value sign, which is not entirely where we want to be. But first, I'm going to do a little bit of algebra on the right side. So we're adding inside that exponent. So I could rewrite on the right side, since we're adding in the exponents, as a product. I've got e to the c1 times e to the 1/2 t squared. Now, it makes sense, I hope, looking at this equation, that what's on the right side has to be positive. because e to the c1 has to be a positive constant, right? I've got a positive base, raise it to any real number power, it's going to be positive. But x plus 1 itself could be positive or negative, right? It's stuck inside absolute value. So once you take the absolute value, of course, it's going to be positive. In order to kind of free this equation, to free that expression on the right side from being inside absolute values, all we're going to do is substitute this substitute that constant, e to the c1. If c1 is an arbitrary constant, then e raised to the c1 power is an arbitrary positive constant. In order to allow for that x plus 1 itself to be positive or negative, we're just going to replace this with some other constant. So x plus 1, now no absolute values, is some constant, I'll call it c, e to the 1/2 t squared. So e to the c1 is an arbitrary positive constant. We're replacing it with the constant c. We're also dropping the absolute value signs at the same time to allow for the fact that this could be positive or negative, and that's fine for our function. And whilst we can't say c is exactly equal to e to the c1, we do know that c is equal to plus or minus e to the c1. Like, we could say that for sure. And then one last thing, we'll just subtract 1 from both sides to get x by itself. So x of t as a function is c e to the 1/2 t squared minus 1. Again, look where that arbitrary constant ended up. You know, our final result is not just some function of t and then plus a constant at the end. This time, that arbitrary constant, as we kind of worked through it to find our solution, ended up as a coefficient on that exponential term. I'm going to pause there for a moment and see if there are questions on this.
My question is just, why can you drop the absolute value?
Why can we drop it? So think of it like the absolute value of x plus 1. X plus 1 could be positive or negative, right? So I've got some function x of t. And when I take whatever that is, add 1, and take its absolute value, so the question was, I don't know if you turn your mic on, the question was, how could we drop the absolute values? So whatever that function is of t, if I add 1 and I take the absolute value, it gives me this function, which has to be positive, right? I mean, it has to be positive, first of all, because this is absolute value. It makes sense that to have this constant here. C1 could be any old constant, positive or negative, doesn't matter. It's an arbitrary constant. E to the C1 just has to be positive because of the nature of the exponential function. So if I'm trying to get x by itself, I'm allowing for the possibility that it could be positive or negative. Like, how about, I'm going to do a little bit of stuff in the margins. So I'm going to go way back. Absolute value of x is either positive x or negative x, right? Like, the absolute value of something is either going to be itself or the negative of itself, right? The absolute value of 5 is 5. The absolute value of negative 5 is 5. It's the negative of itself. So you can drop absolute values on something if you put a plus or minus in front of whatever it's in, whatever whatever the expression is that it's equal to. It's not that it could be either or, it's that it would be one or the other. So if here's the intermediate step, I guess I could have included right here, is that if absolute value of x plus 1 is e to the c1 times e to the 1/2 t squared, that means that x plus 1 is either, has to be one of these two things. It's either e to the c1 times e to the 1/2 t squared, or it's negative e to the c1 times e to the 1/2 t squared. So It could be positive or negative, but the idea is just you just change whatever that constant is. Now, if I know added information about the function, we would be able to find what value c takes on. We don't have to worry about a positive or negative. But if I just kept e to the c1, I would be saying that the whole thing is positive. So this step here where I go, like, I'm not just dropping the absolute value signs. On the right side, I'm also saying I can't just write it as e to the c1 anymore, because that would force it to be positive. So I have to acknowledge that this could be positive or negative, and that's why I replace e to the c1 with just arbitrary constant c. That was kind of windy, but did it answer your question?
Yes, thank you.
Okay. Are there other questions? Okay. Let's try another. So here's an initial value problem. We're going to get the general solution and then use that initial value to find the particular. But first, we just start with our focus on this differential equation. What do we do first?
Rewrite it as x to the negative 1. Divide it.
Oh, like,
Dx equals.
hold on one second. Did you turn your mic on when you said that?
No.
Can you turn it on and say it again?
Rewrite x as x to the negative 1 and
So-
divide it to the other side.
So like that?
Yep.
Okay. So divide it to the other, so divide both sides by x to the negative 1
Multiply by dt.
and multiply by dt. Here, well, hold on. I'll write it this way. Okay, so when we do that, we have dx over x to the minus 1. On the right side, we have t dt. Bless you. Now what? Integrate, yeah. What do we get on the left?
Just x squared over 2, right?
Right, yeah, because this is, in fact, I'm going to rewrite this. This is just the integral of x dx. And so both of those are just power rule. We get x 1/2 x squared and 1/2 t squared. So 1/2 x squared is 1/2 t squared plus a constant. So I'm going to call it c1. I don't know about you, but when I see like this part, once we get to this part where it says, oh, integral x dx equals integral t dt, I think, well, these functions must have pretty similar behaviors, and it almost makes me think they should just be the same function. Let's sort of see how this works out. We want to get x as a function of t, so we have 1/2 x squared equals 1/2 t squared plus c1. I'm going to just get rid of the fractions. I'm going to multiply both sides by 2. So x squared is equal to t squared plus 2 times c1. I'm going to replace that with a new constant c2. Now they didn't ask us to find the general solution x of t, so I'm going to bypass that right now. I'm not going to solve for x directly just yet. They just wanted us to solve the initial value problem. So I'm going to take the opportunity now and plug in that initial value that they gave us. They told us that x of 0 is equal to 1. So that means that 1 squared is equal to 0 squared plus c2, and I know that c2 is equal to 1. And I can plug that back in and get x squared is equal to t squared plus c2. What we have here x squared equals t squared plus 2. This is what we would call the implicit solution. It does relate x as a function of t, more or less, but it's not solved explicitly for x. It's solved for x squared. If I want to get x by itself, I take the square root, so I have to have a plus or minus square root t squared plus, we know what C2 is, right? Let's go ahead and put that in. Plus 1. And this is the explicit solution. That's x, or x of t if you want to be clear about that function notation. Either's fine. When you're asked to solve a differential equation, your goal, unless stated otherwise, will be to get an explicit solution. Questions on that example? Okay. Some differential equations are not separable at first, but could become separable if you make a clever substitution. One type of substitution that works that works with some frequency is letting u equal x over t. So this equation here really is not separable. It won't be possible to write this as, like let's say if I get the x prime by itself, right? So in that definition of separable, we have the x prime by itself. Let's do that. If I divide both sides by t, then we have x prime equals 1 plus x over t. That's not separable. I can't just write that right side as something with only t's times something with only x's. But if we let u equal x over t, then notice that I'm going to do a little algebra and a little calculus. Let's multiply both sides by t, so x is equal to u times t. And now we're going to differentiate with respect to t. So if I differentiate with respect to t, then on the left side we have dx dt. On the right side, we have to use the product rule. So the product rule would have us, let's see, first times derivative of the second, so that would be du dt times 1, plus second times derivative. Oh, I just did that backwards. It works out either way, but I'm just going to do it the way I said it. First times derivative of the second, so that's u times 1 plus second times derivative of the first, du dt. There we go. So that's our dx dt. So I'm going to replace that. I'm going to substitute that in for our x prime here. So on the left side, I'll have u plus t du dt. On the other side, I've got 1 plus x over t is u. I've gone from an equation with x's and t's to one with u's and t's. Let's subtract u from both sides. So t du dt is equal to 1. Can we separate the variables here?
H of x be 1 and g sub t or whatever be 1?
Yeah, so let's see, if we got du dt by itself, then we'd have 1 times t. So yeah, like the h of x would just be the constant function 1. Mm-hmm.
It'd be 1 over t, wouldn't it?
Oh, yes. Thank you. So now how do we separate them? I want all my u's on one side and just the t's on the other.
Du equals dt over t.
Mm-hmm. So we have separated the variables. We're ready to integrate. I'm going to actually scroll up really briefly and just add one thing that I meant to point out in the very beginning. I added an initial condition after I printed these out. So I even highlighted it on my paper copy so I would remember to tell you right in the beginning of this example. And then I didn't until just now. But back to the fun stuff. So now we're ready to integrate. What does this result in? What's our next equation?
U equals ln t plus c.
Is your mic on?
U equals ln t plus c. Absolute value ln t.
Ln of absolute value t, yeah, plus a constant. So now we have u as a function of t. We want x as a function of t. So we're going to go back and use that substitution again. So we know that u was x over t. So we'll plug that back in. If I want to get x by itself, that's not terribly difficult. We just need to multiply both sides by t. There's a general solution. We could find the particular solution by using the initial condition, the initial value. So x of 1 equals 5. So that means that 5 equals ln of 1 plus c1 times 1. What's ln of 1? Oh, you know, let's see.
Isn't it 0?
It is 0, yeah. I just want to make sure if folks in Randolph are trying to. I haven't heard anything from Randolph, so if you've been speaking and I haven't responded to you, that's because I haven't heard anything. So just make sure your mics are turned on. Ln of 1 is 0, and if you're having problems with your mic or something, if you're having any difficulties, let me know and I'll ask Asher to look at it. So we get 5 equals c1. There's our constant, that parameter. So now x of t is equal to ln absolute t plus 5 times t. Questions? Okay. We're going to do one more today that requires a substitution. So this time they don't tell us what substitution to make. And this one's not an initial value problem, so we're just going to find a general solution to this one. But we're starting out dx dt is equal to x plus 4t squared. It's not separable. I mean, I think pretty quickly we can see we're not going to be able to separate that out as a function of x times a function of t. But we can make it separable if we make the substitution u equals x plus 4t. Like we did before, we're going to differentiate this with respect to time. So du dt is dx dt plus 4. And then I'm going to rearrange this to get dx dt by itself. And I'm doing that because I'm trying to find, I want to be able to replace this dx dt with another expression. So dx dt is du dt minus 4. Minus 4. So I want to go from this equation with x's and t's to one with just u's and t's. I don't want any x's left at all. I know it's going to go on the left. It's that thing we just found over there. So dx dt is du dt minus 4. What's on the right?
U squared.
U squared. Did you turn your mic on?
U squared.
Yeah, great. Randolph, is it Randolph who said that?
Yep.
Yeah, Randolph gets the credit because Randolph turned their mic on.
What?
Okay, so now let's just rewrite this. I'm going to get du dt by itself now. So du dt is u squared plus 4. And this is not too hard to separate now, right? We're going to get the dt. We're going to multiply by dt because that's never on the bottom. We always know we're going to do that. And we want the u's with the du, so we'll divide by u squared plus 4. And what we end up with here is du over u squared plus 4 equals dt. And you know, this is the point, now that they're separated, this is the point where we say, okay, let's integrate. So, okay, let's integrate. The right side's pretty simple, but how do we do the left side? Anybody recognize that form?
The arctan.
It's the arctan. Yeah, good. So you might recall, and if not, it's probably on that sheet that I handed out the first day that you got, but the integral of du over u squared plus a squared is 1 over a arctan u over a plus a constant. So, so this is going to be 1/2 arctan of u over 2. And I'm going to, just like we always have, I'm going to reserve the arbitrary constant for the right side. And the integral of dt is just t plus a constant. I'll call that C1. Now what? Like, what's our goal? Right? I mean, we integrated. That's definitely a success. Like, we need to get that far when we're solving this. But now we have this equation with u's and t's in it. What's our, like, ultimate goal in this problem? If we're, like if we just look at the original equation here that we started with, it says solve. What does it mean to solve a differential equation? What is it that we're looking for?
Solving for x, aren't we?
Say that again?
Are we solving for x?
Yeah, we want x as a function of time, right? We want to find x of t equals. We want some function of time of t that satisfies this. So look at where we are. We have this equation with u's and t's. We want to get to x's and t's. In order to get that, we're going to have to make our substitution back, like substitute u back in with that expression with x's, x's and t's. I think what I'll do first is solve for u, right? Figure out what u is, and then I'll make this. I could make the substitution first. I think as far as just overall like cleanliness of approach, I think it'll be a little bit neater to solve for u first. And I'm going to multiply both sides by 2 just to clear that fraction. So arctan of u over 2 is equal to, I'm going to distribute 2t plus, and 2 times an arbitrary constant is another arbitrary constant. I'll call that C2. Now if arctan of u over 2 is equal to 2t plus C2, how do I extract u from that?
Tan on both sides?
Yeah. Right, if arctan of u over 2 is equal to 2t plus c2, that means that u over 2 is tan of 2t plus c2, just by the definition of arctan, which we could also realize, as I think, I don't know who said it, but stated it as take tan on both sides. Like we could take the tangent of both sides. And when a function meets its inverse function, they, annihilate each other, and we just get the argument inside. So now easily we get we figure out what u is, right? We're just going to multiply by 2. So u is 2 tan of 2t plus c2. Now we can go ahead and use our substitution. U is equal to x plus 4t. And now solving for x is pretty simple. We'll just subtract 4t from both sides. So now x of t is equal to 2 tan of 2t plus c2 minus 4t. Fun? Mostly. There are some practice exercises which I encourage you to work through. So these are the ones from the section we finished before. This was the new stuff today. It's on page 26, and I have, like I said, I did post that PDF, the exercises. So there's a PDF of just the exercise pages, and then if you go back to the modules, right at the top module, I have the pages that have the answers to the odd numbered questions are right here in that top block. And that's for the whole text. So I'm only going to post the exercise pages going forward while the book is still on back order, but the answers will always be there. And I think if I saw it correctly, I left it back in my office, but I think they even might include some steps, and we all know, of course, the answers, the solutions that the textbook puts forward are always imperfect, and that if they show steps, they definitely skip steps. But I think some of them even include some steps. If you have questions on any of those, let me know. please go and print out the assignment and, start early. And if you're stuck, ask questions. I'm going to take the first part of class on Monday to go over questions that you might have on either the practice or the assignment. So enjoy the weekend.